Welcome back to the Algebraic Graph Theory Seminar. This week we have Steve Kirkland, and he'll be talking about state transfer for paths with weighted loops at the end vertices. You need to unmute yourself, Steve.
Okay. Audible and visible. Thank you so much. I love technology. I'm going to talk today about some preliminary work results that I've worked up with my postdoc, Christopher Van Bommel. So this is very much a work in progress, but I'll try and emphasize sort of the bigger ideas and not the fine details, just so that you can get an idea of what we're thinking about right now. So we're going to be talking about state transfer for paths that have weighted loops on the end vertices. And so if you don't know what any or some of those words mean, I'll try and give you a short introduction just to get started. So the motivation for the problem under consideration is a problem in quantum computing. Essentially, it's a model for quantum communication that was described by Bose. And he posits the notion of a quantum wire for transferring information. The idea is that this might be something like a quantum data bus inside of a quantum computer. Since I don't know any physics and I'm too scared to learn anything about it, what I'll do is I'll try and talk about things more in terms of graphs and matrices. So here's the setup. We have an undirected graph on n vertices, and the vertices represent quantum spins. And if there's spins that are interacting, then we represent that as an edge in our graph. And so here's the idea. I'm going to take two vertices, or equivalently two spins. So a sender vertex, which I'll call S, and a receiver vertex R. And so we input a quantum state at vertex S, and then we engineer these physical couplings between the spins and so that they can be made to interact with each other as represented by the graph that we have in mind. And after a time t is elapsed, the unknown state is communicated to vertex R, and it's read out. And we hope that whatever we put in at time 0 at the sender vertex is close to whatever we're reading out at time t at the receiver vertex. Okay. And so you have this notion of how close the initial state is to the state that's read out, and that's measured by what's called the fidelity. And so that's a number between 0 and 1. It depends on t, the readout time, so it's a function, f of t. It measures the similarity between the sending state and the receiving state. So f of t is equal to 1 corresponds to exact communication of the state, and f of t near to 0 corresponds to poor communication. And so it turns out under certain, I am informed, reasonable physical hypotheses, the dynamics of the communication are described by what's called a continuous time quantum walk on the graph that models the network. Okay, so I'm gonna say a bunch of that stuff again, but in more mathematical language. So let's set it up like this. We have our graph G. It'll be on vertices that are labeled from 1 to n. And we have a corresponding 0, 1 adjacency matrix A for that graph. And so it turns out that if we have identified our sender vertex S and our receiver vertex R, then the fidelity at time t is given by the following quantity. So here's what I do. I take the matrix exponential of I, so I is the square root of -1 here. So I times t times A. I look at the entry in row S column R of that matrix, and I take the modulus, the complex modulus of that number squared. Okay. And so it turns out that the exponential e to the ita turns out to be a unitary matrix. And so, of course, that means the sum of the square of the moduli of the entries across each row is equal to 1. And so you can think of each of those individual moduli squared as representing a probability distribution that depends on time. And so hence we have this language of the quantum walk on G, kind of reflecting in a sort of philosophical ways something like a random walk on a graph. That's where the motivation for the term comes. And so in terms of the quantum walk interpretation, the fidelity can be thought of as the probability that quantum walk on the graph starting at vertex S arrives at vertex R at time t. All right, so that's a little bit of background and context. And so I want to focus on a very restricted set of graphs for the remainder of the talk. So we're going to think only about unweighted paths. So when I say unweighted, I mean I've got a path. I'll take the convention that it's always on n vertices, and I'll take the convention that the vertices are labeled so that vertex j is adjacent to vertex j plus 1 for each j running from 1 to n minus 1. Okay. And I'm going to focus even more so by looking at state transfer from one end vertex of the path to the other end of vertex of the path. Okay, and part of the motivation for that is that somehow the path is this minimally connected structure, and I'm trying to if I'm trying to activate some of this state transfer business. I'd like to do it over long graph theoretic distance, because somehow that's a proxy for the physical distance between the spins in the quantum network. Okay, so here's what might happen in the best of all possible worlds. The best case scenario is that there's what's called perfect state transfer from one vertex to the other. So here's the definition. We have this perfect state transfer at time t naught if the fidelity of the state transfer from one vertex to the other at time t naught is equal to 1. Okay, so that would be the thing that we would want to happen, because that corresponds to perfect communication of the quantum information in the network that we're trying to model. Okay, so that's a great objective, but there's a bit of bad news on that. It's been known for quite some time that the only paths for which we have perfect state transfer from one end vertex to the other are the paths of on 2 vertices or on 3 vertices. Okay, so that's a little bit disappointing. We had a great idea that we'd like to have this perfect state transfer, but it's not available for a path of length on 4 or more vertices. Okay, so let's regroup a little bit and think about what would maybe the second best scenario be. And so here's another notion that's also been well studied. That's the notion of pretty good state transfer. So our network has pretty good state transfer from one vertex to the other if there's a sequence of times t sub k, so that when I evaluate the fidelity f of t sub k, that converges to 1 for this subsequence as k goes to infinity. Okay, so we're not going to have perfect state transfer in our path, but we might hope that there's pretty good state transfer so that the fidelity can be made arbitrarily close to 1 by suitable choice of the readout time. All right, well, here's another result on that. There's pretty good state transfer between n vertices of the path on n vertices, if and only if n plus 1 is either prime or twice a prime or power of 2. Okay, well, that's not exactly the disastrous disappointment of the earlier result on perfect state transfer, but it's kind of mixed news. I mean, it says that something super special has to happen with the number of vertices in order for this pretty good state transfer to be available to us. Okay, What I want to do now is I want to think about a variation on the kind of graph that we're talking about. I said I was interested in paths. And so let's maintain our interest in paths, but I want to pick up on an idea from some work of Kempton, Lipner, and Yao that goes like this. Take your path, by all means, take your path on n vertices, again, unweighted, and now add a loop of weight w to each of the two n vertices of the path, okay? In terms of a physical interpretation, Kempton, Lipner, and Yao think of this as enforcing an energy potential at each of these two n vertices. But for our purposes, since we're thinking in like algebraic graph theorists, we're just going to think about a weighted loop of weight w at each of the two pendant vertices. Okay, I should say before I go any further here, that this work of Kempton, Lipner, and Yao contains a lot more mathematics than just the thing I just told you. Okay, they in fact think about a much broader family of variations on the path. But I'm going to stick to this simple case that we have a path with these two extra loops added at the end vertices. Okay, so if you delve into their work, they show that if n is greater than or equal to 4, perfect state transfer from one end vertex to the other is not possible. Okay, again, another little disappointment, but on the other hand, maybe not so unexpected now that we know a little bit about some of the earlier work on the topic. But they also show that if W happens to be transcendental, the weight of the loop is a transcendental number, and for any n greater than or equal to 2, there's pretty good state transfer from one n vertex to the other. Okay, so I'm going to view this as good news. I mean, the transcendentals are dense, and so there's lots and lots of choices of good values of W. There's a dense set of W values for which pretty good state transfer between the n vertices takes place. Okay. However, Christopher and I have shown that at least for the path on 4 vertices, it's also the case that for any positive choice of W, there is a sequence of WKs that converge to your target value W. But when you put the loop weight at WK for your path, there is no pretty good state transfer between the n vertices. Okay, and so what that means is there's also a dense set of W values for which pretty good state transfer for the n vertices fails in the case that we have a path on 4 vertices. All right, well, so far this talk seems to have been mostly a thing of me kind of building up your expectations and then deflating them. And so, I don't want to keep going through that sort of psychological roller coaster. And so what I'm going to do is I'd like to change the objective for now. So I still want to think about a path on n vertices. I still want to think about adding the loops of weight W at the n vertices. But let's scale our expectations way back, because in some sense, what we learned from the previous 2 examples is that it may be a mug's game to try and pick the nice value of W that is going to give you pretty good state transfer. So why don't we just think about it in a slightly different way? Why don't we set as our objective, let's find a W and an N so that we can guarantee a certain lower bound on the fidelity, and so this will be the fidelity of state transfer between the n vertices, and also know which values of the readout time t will get us that decent fidelity. Okay, so this is very much weaker than pretty good state transfer. On the other hand, I want to have some sort of guaranteed lower bound on the fidelity and some notion of when the readout time should be. Okay, and so that's really what I'm going to talk about for the rest of the seminar today. Okay, so when in doubt, open up MATLAB. So here's what I've got. just as a way of trying to get my head around what's going on here. So I've taken some small values here. I'm looking at the path on 10 vertices. And I'm taking the weight of that loop on each end vertex as 2. And now I've plotted the fidelity of state transfer from one end vertex to the other for the values of t between 0 and 50. And if you've ever done any of these MATLAB plots, they all kind of look the same. They all kind of look like this. So it's some noisy something or other that doesn't have a lot of nice structure. And in particular, looking at the peak values here, which are, I think, less than 0.06, we also see the fidelity is quite crummy for this range of values of t. Okay, so maybe I haven't learned very much from taking this shorter window, but what if I go to a longer window of time values? So I'm keeping the same parameters. So I'm still looking at the path on 10 vertices. I'm still taking my loop weight as 2. And now but I've very much expanded the range of values of t for which I'm reading out. Okay, again, these are MATLAB computations, so take it for what they're worth. But here's what you see. Definitely still noisy out as we saw before, but because we sort of backed out on the time scale here, I hope you can see that there's some kind of structure there. In particular, there seem to be a couple of pretty good peaks for the fidelity where they're at least getting close-ish to 0.9. And there also seems to be some structure to the readout times where those peaks are. Okay, and so in some sense, the rest of this talk is me trying to understand this picture. Okay, so let's just set up a little bit more of the mathematics of it. So I'm going to focus only on values of W that are strictly bigger than 1. You'll see when some of the results come out, you'll see why I need that convenience. And then the adjacency matrix we're looking at is the guy I'll call A of W. And of course, this is just the same as the adjacency matrix for the path, but then I've tacked on in the 1, 1 and the n positions, I've tacked on that value of W to represent the loop weight. Okay, it's well known that this is a tridiagonal matrix that's irreducible, and so the eigenvalues are distinct. And so we'll just label those eigenvalues as lambda 1 down through lambda n in strictly decreasing order. And I'll produce the eigenmatrix, the orthogonal eigenmatrix for A of W, I'll call it V. And here I'm thinking that the jth column of the matrix V is associated with the eigenvalue lambda j, okay? For notational simplicity, I'll suppress the explicit dependence on both W and N in most of what I write out here. Okay, and so then, in fact, the fidelity expression comes up a little bit more nicely. If I want to know what the fidelity of state transfer at time t from vertex 1 to vertex n is, okay, it looks like this expression here. And I've sort of buried a bunch of information into that expression, and it comes out of the fact that since our adjacency matrix is centrosymmetric, there's nice structure to the eigenvectors. When you're thinking about this matrix exponential, the successful way to think about it is in terms of the eigenvalues and eigenvectors of the matrix A of W, and you come up with this expression. And so then what you see is, if I want to understand what's happening with the fidelity, I need to get a grip on two things. I need to know something or other about the eigenvalues of this matrix, the lambda j's, and I need to know something about the entries, or in fact, the squares of the entries in the first row of the eigenmatrix V. Okay, and so I sort of said this earlier, but I'll say it again. I'm only going to emphasize the general ideas only. I'm not going to give you the full mathematical details. And the reason is that they're formula heavy. It's summer where I am, it's sunny out, and we don't want to do a lot of heavy lifting this early in the week. So I'll give you sort of the flavor of the results without the full-on technical detail. I think you will thank me for that later. Let's see. Okay, so let's take a look at some information about the eigenvalues. Okay, so it turns out that lambda 1 is always bigger than w plus 1 over w, and that in turn is bigger than lambda 2. All right. And in fact, you can do a little better than that. The values of lambda 1 and lambda 2 are actually close to w plus 1 over w. So they're of the form w plus 1 over w from plus some stuff that goes to 0 faster than 1 over n. And in fact, it turns out, as we'll see later on, way faster than 1 over n. Okay, so we have these two leadoff eigenvalues, lambda 1 and lambda 2. How about the other eigenvalues? Well, this will not be surprising to those of us who've worked with the adjacency matrix of the path. So for each j between 3 and n, I can find a value of theta j that lives in the interval between pi times j minus 2 on n minus 1 and pi times j over n plus 1, so that the eigenvalue lambda j can be written as 2 times the cosine of theta j. Okay, the values of the theta j's specifically depend on the loop weight w. And if you've ever taken a look at the closed form expressions for the eigenvalues of the path without loops, that's very reminiscent of those kinds of formulas. Okay. So that's a bit of information about the eigenvalues, and they seem to fall into two distinguished sets. Lambda 1 and lambda 2 seem to be doing one thing, their own thing, and then the remaining eigenvalues are doing something else. All right. How about the eigenvector entries? Well, we can come up with expressions for the first and second, or I should say the squares of the entries in the first and second positions of the first row of the eigenvector matrix. Okay, so v11 squared and v12 squared both look like w squared minus 1 over 2w squared plus some stuff that's on the order of 1 over n. Okay, so a bunch of the mass in the first row of that eigenmatrix is concentrated in the spots where we are looking at the lambda 1 and lambda 2 eigenvectors. And then remember that eigenmatrix, it's a, whatever it is, a unitary matrix or something. So the remaining, the sum of the squares of the remaining entries in that first row have to sum up to something like a 1 over w squared plus some stuff that looks like 1 over n. Okay, so those are the sort of back of the envelope estimates that we have for eigenvalues and eigenvectors. And I'll just give you a little a glimpse of some of the techniques that Christopher and I are using to generate these results. So for lambda 1 and lambda 2, essentially you can work with matrices of roughly half the size of the original matrix A of W. If n is even, then lambda 1 and lambda 2 are the largest eigenvalues of this matrix and this matrix respectively, each of half the size. And if n is odd, there's a slight variation. Lambda 1 is the big eigenvalue of this guy here of order n plus 1 over 2. And lambda 2 is the big eigenvalue of this guy over here of order n minus 1 over 2. This comes out of the fact that there's some nice symmetry properties for the eigenvectors. And so essentially what it's saying is that the top half of the eigenvector is intimately related with the bottom half of the eigenvector. And you can come up with some simplifications that way. And then those matrices that I have on the screen there are actually reasonable to work with. The corresponding eigenvectors are positive because these are essentially non-negative matrices. And the entries of the eigenvectors obey some nice recurrence relations, as you would expect with tridiagonal matrices. We often see lots of connections with three-term recurrence relations. Okay, so that's kind of a little bit of a glimpse as to how we come up with our estimates for lambda 1 and lambda 2. Okay, technique for the eigenvectors is a little less pretty, but workable. So here's what I'm going to do. I'm going to build this matrix Q made up out of sines of certain angles, and I'll make this matrix D which is a diagonal matrix with some 2 times some cosines living on the diagonal. I'll sort of, I'm not trying to be mysterious about this at all. This is known stuff. Q times D times Q transpose is the adjacency matrix of the path on n minus 2 vertices, whose eigenvalues and eigenvectors are known. Okay, and so then I can write out my A of W, okay, my adjacency matrix for the path with the loops added. I can write it out like that, where all I've done is I've put the eigen decomposition in the 2-2 block for P sub n minus 2. And then we just try and think about how you would write out a lambda 1 eigenvector. Well, one way of writing out a lambda 1 eigenvector is like this. You just work with the equations. So I'll have ones in the first and last positions of that eigenvector. And then the guy in the middle here is this u, which I can write out as q times lambda 1 times the identity, take away t inverse times q transpose. And I take the first and last columns of that guy and sum them up. So why is that helpful? Well, it turns out that this u transpose u, which is sort of the key part of the formula here, is essentially, it's a Riemann sum for a certain not very nice integral that we can then evaluate. And when you evaluate that integral, you outplops the estimate for v11 squared. Okay, and that order 1 over n term that you saw in the formula that I gave you, what is that? Well, that's the error in the difference between a Riemann sum and the actual value of the integral. Okay, so that's where that comes out. The estimate for v12 squared is done in very much a similar fashion. Okay, so that's just a little bit of information on the techniques. And so now here's what we want to do is try and figure out, okay, what can we do with this? So let's take a look at the fidelity. Okay, I'm going to do nothing more complicated than the triangle inequality here. So the triangle inequality, so all I'm doing here, remember the fidelity is this, it's the absolute value square of this certain big sum. And I'm just going to parse out 2 pieces. The part of that sum in the fidelity that corresponds to lambda 1 and lambda 2, and the part of the sum that corresponds to everything else. Okay? And so that's an upper bound on the fidelity. And in a similar way, we can also produce a lower bound on the fidelity. I need a little extra assumption here. As long as this expression here, so essentially what I'm doing is I'm parsing out the bit of the fidelity sum that corresponds to lambda 1 and lambda 2, and here's an estimate for that corresponds to all of the other eigenvalues. As long as that expression is non-negative, then I get this lower bound for the fidelity at time t. Okay, well, that's pretty incomprehensible. So what I want to do is go back and use our sort of ballparky estimates for the entries in the first row of the eigenmatrix. And so to do that, I'll just set x to be the value of the readout time t times lambda 1 minus lambda 2. Okay, and so now you just work out using the estimates on the entries in the eigenvector. The fidelity is at time t is bounded above by square root of 1 minus cosx on 2 times w square minus 1 on w square. Okay, so what is this? This is essentially our estimate for the piece that corresponds to lambda 1 and lambda 2. Okay, and then here was our other estimate, the sums of the remaining entries in the first row of the eigenmatrix, and then our error term of 1 over n. And then you can just use a little bit of work with the half angle formula to neaten up that coefficient. So I get the absolute value of sine x on 2 times w square minus 1 over w square plus 1 over w square, the whole thing squared, plus my error term of 1 over n. Okay. And so that's the upper bound on the fidelity. here's the lower bound. Again, I need to assume that the stuff inside these brackets here, this stuff has to be non-negative. Okay, and essentially what that means is that cos x can't be too close to 1. But as long as that's non-negative, then I get a corresponding lower bound on the fidelity of absolute value of sine x on 2 times w squared minus 1 on w squared minus 1 over w squared, the whole thing squared, plus 1 over n. Order of 1 over n. Okay, so again, just to emphasize what the details are, this is a sort of a two-step process. It's the estimates on the eigenvector entries, and then nothing more sophisticated than a triangle inequality. Using a similar technique, which I won't go into, it's also easy to, well, it's not that easy, it's showable that if w is bigger than the square root of 2, and I take any natural number k, then if I look at the fidelity evaluated at the readout time 2k plus 1 pi on lambda 1 minus lambda 2, that is bounded below by w squared minus 2 divided by w squared, the whole thing square. Okay, so that is exactly the thing I wanted to accomplish. I mean, what I've said here is, as long as my w is at least a little bit big, I have a guaranteed lower bound on the fidelity, all right? And I know when I should read out to get that guaranteed lower bound on the fidelity. So in some sense, that's pretty good news. The other piece of the puzzle is, if you just look at that guaranteed lower bound, you can see that if w is big, I can push that lower bound close to 1. All right, so by suitable choice of w, I can guarantee a certain value of fidelity at a particular readout time. Here's the other thing I want to point out just while we have the formulas on the screen. I showed you that big graph where there seemed to be a sort of a periodic structure to the noisily periodic structure to the fidelity graph. Well, maybe that's kind of explained by some of the formulas here, right? I've got a sine of some stuff as an upper plus a term of 1 over w squared as an upper bound, and a sine of the same stuff minus a 1 over w squared as a lower bound on the fidelity. And that suggests that there's some noisily periodic behavior we might observe. Okay. Let's talk a little bit about readout time. And in some sense, this is sort of a partial converse to what I just told you about the odd multiple of pi on lambda 1 minus lambda 2. So let's suppose that I've got a positive value of epsilon. And here I want to think about epsilon as being small. And let's suppose for concreteness that 1 minus epsilon is bigger than 1/2 plus 1 over w square. Okay, again, I need w bigger than the square root of 2 here for this to be sensible. And I want to know, let's suppose that we had a readout time t, so that the fidelity at time t was at least as big as 1 minus epsilon. I would like to know what time that is. Okay, so here's the conclusion, and this was really just working with that upper bound on the fidelity that I showed you a couple of minutes ago. So then the readout time has the following form. It looks like some odd multiple of pi plus tau on the top, divided by lambda 1 minus lambda 2. And we have a grip on how big tau is. Absolute value of tau is bounded above by the inverse cosine of this expression here. So it's twice the root of 1 minus epsilon, take away 1 times w squared minus 1, divided by w squared minus 1, and then plus our standard error term of something like 1 over n. Okay, and again, I want to look inside of that expression there. Imagine what happens when epsilon is super close to 0. Okay, so when epsilon is close to 0, we're looking at the inverse cosine of the number 1. We're looking at the inverse cosine of the number 1. Okay, and that's close to 0. All right, so what we're seeing here is if my readout, if I have a readout time t so the fidelity is at least 1 minus epsilon, and epsilon is small, then my t-value is something like close to an odd multiple of pi divided by lambda 1 minus lambda 2. And in fact, you can work with a slightly sharper version of that readout time expression that I showed you. Imagine we're in a situation where we've, by some good fortune, we've chosen a value of W so that pretty good state transfer from one end vertex to the other holds. Okay, so let's look then at a sequence of readout times T sub j so that f of tj approaches 1 as j goes to infinity. Let's try and think about what those readout times look like. Well, the same sort of techniques that we've been using already says that there are sequences of natural numbers k sub j and values, sequence of values tau sub j and 0 pi, so that the tj's look like twice kj plus 1 times pi plus tau j, all divided by lambda 1 minus lambda 2. And moreover, those tau j values go to 0 as j goes to infinity. Okay, so if I've got a W value that gives us pretty good state transfer, then the good readout times that give us fidelity close to 1 are closer and closer to odd multiples of pi on lambda 1 minus lambda 2. All right. So what we're saying then is, if our fidelity is close to 1, the good readout time looks like satisfies an equation of the type lambda 1 minus lambda 2 times t is, roughly speaking, an odd multiple of pi. Okay. Here's a sobering thought. We've also been able to show that lambda 1 minus lambda 2 is tiny. Okay. Order of magnitude is 1 over w to the n minus 2. Okay. So if w is big or n is big, the gap between lambda 1 and lambda 2 is very small. And that means is that the readout times that we need to get to have half-decent fidelity are very large. Okay. Well, take it for what it's worth. Here's some more MATLAB computations just to get a sense of what things look like here. So I've just taken a few small values of n, okay? I've taken values n equals 5 and n equals 10, and some small values of w, 3, 4, and 5. And then I've just given you a bunch of information here. So the third column here tells us what pi over lambda 1 minus lambda 2 looks like. That's essentially the first time you would expect a decent fidelity, that readout time. Here's the fidelity computed at that readout time. Here's the lower bound that we had before, this w squared minus 2 over w squared, the whole thing squared. And then I've also computed what I call T max. What's that? Well, here's what I've done. I've gone through numerically. I've computed the fidelity at time t for values of t between 0 and 2 pi over lambda 1 minus lambda 2. And then T max, that's the time that gives me the biggest of those fidelities. So here's T max, and here's the corresponding fidelity. And so let's just take a look. So notice that the values in the third column here, pi on lambda 1 minus lambda 2, and the value at this T max, sorry, the value of T max is, they're certainly in the same ballpark as each other, which is what we expect. The other thing to notice is that it seems to me, at least in these small examples, the values of the fidelity at pi over lambda 1 or minus lambda 2 are not nearly as good as the values at T max. Okay, so reading out at pi over lambda 1 minus lambda 2 is guaranteed to give you something, but it may not give you something that's very close to the maximum possible fidelity. Okay. So that's just to sort of get you a sense of what the orders of magnitude look like for these various quantities of interest. So I'll just wrap it up. As I said before, we saw in that that picture that I showed you for n equals 10 and w equals 2 and t running over a large interval, that there was this noisy periodicity. And as I said, that's explained by the fact that our fidelity bounds are something like, I mean, the fidelity bounds are essentially a sine function, absolute value of a sine function times something that, at least as w is large, is pretty close to 1. And so that, I think, explains at least some of that picture. From the numerics that I just showed you, the lower bound that I gave you on f of pi over lambda 1 minus lambda 2 seems like it's a little bit pessimistic. It seems like we might be able to do a little bit better. That said, it's not 100% plain to me exactly how we would proceed to improve that lower bound. And just to give you a peek, I said I was going to spare you most of the horrible formulas. I'll just give you one so you can see what we're dealing with here. So in fact, we produced the closed form expression for v11 squared. Okay, there it is. So all I'll tell you, all I'll do is encourage you to just look at this, the sum part here. As I said earlier, this is like a Riemann sum. It's not exactly a Riemann sum because the lambda 1 has an implicit dependence on the number n here. So, but it's like a Riemann sum, and so it's those sort of estimates that give us our expressions for estimating v11 squared and something similar for v12 squared. And as you might expect from the earlier part of the talk, the news is mixed, right? So we do get a guaranteed lower bound on the fidelity, but what we know is those good fidelities only ever come at large readout times. And so with that, I'll stop and thank you for your attention.